For this last earthquake lecture, we're going to talk about the effects of earthquakes, so what happens in terms of damage that's caused by earthquakes. So that's kind of the theme of our last lecture here. You do have a quiz again that you'll be taking with this one, and I'll point you to the correct questions in a minute. So what I'm going to do is basically just do a list of hazards that are associated with earthquakes. We're going to start with the first and foremost. It's just the shaking of the ground. But the more sciencey way that we refer to this is ground acceleration. So basically, if you ever experience an earthquake, what is happening under your feet as those seismic waves, the primary and the secondary Love and Rayleigh waves, are moving through the ground, they actually cause the ground to accelerate. Just like if you're in a car, you press the accelerator, the ground is doing, or the gas pedal, the ground is doing the same thing. So that's called ground acceleration, and that's the forces acting on an object in motion. But the way that you can think about this is that the ground under your feet is literally accelerating, just like pressing a gas pedal. So, as a sense of scale, we usually measure ground acceleration in terms of G's. That would be the unit. So 1 G of force would be equivalent to, like, if you're on a roller coaster and you drop to the bottom of the first hill, like in the image here on the left side, you feel about a G of force pushing down on your body at that point in time. As another example, a half G, if you have a car that can do a burnout quickly and your body flies backwards, then you're feeling about a half G of force. Or if you were in a rocket launch needs about 3 Gs of force to get it to escape the atmosphere. So that's ground acceleration, but what does it actually do? It is what is responsible for toppling over buildings and homes. So, for example, just for some numbers, if you like the math of this, if you have a magnitude 6.7 earthquake, that's about equivalent of 1 G of acceleration. So what that means is that the ground underneath of your feet is moving about 3.2 feet per second. So if you think about that, your house could be in its location, an earthquake could happen, and then within 1 second, now your house has moved 3 feet in one direction, or your house has been uplifted by 3 feet in one single second. So homes can collapse at just 0.1 Gs or 0.1 Gs. That's about equivalent to category 7 on the Mercalli scale. And that would be a very strong earthquake, so difficult to stand, furniture broken, damage negligible, and building of good design, but slight to moderate damage in well-built ordinary structures. So it doesn't take much to collapse a house like this house here. In addition to that, ground acceleration, so if you have a magnitude 6 or greater, as I said on the last slide, that creates about a G of force. So if you have enough force, you can collapse double-decker bridges. So this was from the Loma Prieta earthquake in California. This is a highway interstate bridge that was a double-decker, so it had an upper layer and a lower level, and the upper level collapsed on the lower level during that earthquake in 1989. And then this picture on the right side was from a earthquake that occurred in Mexico in 2017, magnitude 7.1, but basically the ground accelerating or moving underneath the foundation of this building led to the toppling over of that building. So if you want some interesting videos to watch, there's some links that I have here on the slide. So you could look at some YouTube videos. There's one from Japan. There is one from Nepal as well. Just to give you an example, so it's a little bit grainy here, but on the left side, this is Tokyo, Japan in 2011, when the earthquake happened that led to the nuclear disaster. And what you're seeing here is actual footage of the skyscrapers shaking back and forth in response to the earthquake waves or the ground acceleration. On the right side, this was taken from inside of an office building in response to the earthquake happening. You can see how much shaking is actually going on during that earthquake. All right, so that's ground acceleration. Another hazard associated with earthquakes, in addition to the shaking and the damage done by the shaking itself, is landslides. So anytime you have a steep slope or a hill and you get shaking, it is pretty easy, if that hill is made of loose rock or loose soil, it's easy for that soil to just get dislodged and then you'll get landslides. So in places like California, if they have pretty big earthquakes, they can get 40, 50 landslides that happen in a single earthquake event, and then they got to clean it up afterward. These two images here, the left one is from Greece after an earthquake, and then we have Japan in 2011. Earthquake shaking caused this hillside to give way, and then it covered up this road. This kind of aerial footage that's playing through. This is from Big Sur in California. It's just a coastal area in California. There was an earthquake that happened, and it basically dislodged a lot of sediment, and it broke down a highway, or it covered up a highway. So this road right here got covered up and then had to be rebuilt from this earthquake-induced landslide. This one isn't induced by a landslide on the right side, but basically it's just to give you a visual for the type of landslide that can happen when an earthquake occurs. All right, so moving on. So we have landslides, we have ground shaking. A third hazard associated with earthquakes is elevation changes. What I mean by that is that in any given earthquake, if it's large enough, the ground can either raise up by up to 60 feet, or in some cases, it could rise about 100 feet in a matter of seconds, or it could sink down in a matter of seconds. So land can either be pushed up or dropped down, depending on if it's a normal or a reverse fault, by about 60 feet in the largest cases of earthquakes, the largest magnitude earthquakes, in a matter of seconds. So for example, again, this land here the right side used to be up flush with the left side of this image, and then we have these people for scale. So the right side is dropped down relative to the left side. So just two more here. We got liquefaction. So there's a phenomenon that can happen when an earthquake occurs. And if you have a couple of ingredients, if you have water, if you have sand, and you have shaking, you can actually create something called liquefaction. You can do this on a beach as well. So if you ever go to the beach and you go to like the wet, sandy part where the waves are kind of crashing in at the beach, if you just jump up and down, you actually cause the ground to liquefy. The same thing can happen in this process called liquefaction. So the scientific definition of this is that if you have soil and it is saturated, meaning it's full of water, it can instantaneously, the snap of a finger, it can change from solid to liquid during shaking. So what the ground basically turns into is just quicksand, almost instantaneously, snap of a finger during an earthquake. So, for example, in Japan in 2011, these were brand new apartment buildings, and then they were built on sand. That sand was wet when the earthquake happened. So you had sand, water, shaking, and these buildings toppled over. They sank into the sand because the ground underneath of it became quicksand. Same thing here on the left. This is a new roadway, basically where an earthquake happened. It liquefied the road, and this car sank into that roadway. All right. So just to kind of give you the mechanism for it, if you have sand and water, if there is no shaking, basically they're held together and they're packed together nicely underground. But if you add some shaking to it, essentially what happens is that those sand grains will pull away from each other and separate. And if you pull those sand grains away from each other and separate, the ground basically turns to liquid. So any structure that is on that surface is liquefied. The liquefied surface is going to sink into that material. All right, and then the link down below that video is also in your quiz, which you'll see. So here's some evidence of liquefaction occurring. So the one on the top left is from Japan, 2011. The ground kind of looks like it's breathing a little bit, and the water that's coming out is basically because underneath of that sidewalk, the ground has turned to liquid, and that's evidence of liquefaction. Same thing here in Mexico. This is a speed bump on the bottom right, and the speed bump looks like it's breathing. So there was an earthquake. Underneath of this speed bump, the ground is liquefied. So the speed bump is just bobbing up and down in response to the earthquake motion and the earthquake waves. All right, our last hazard here is tsunami. So I assume we're all familiar with what a tsunami is, a gigantic wave that comes from earthquakes. It can also happen if you have a volcano that erupts or if there's an asteroid that hits Earth, you could get tsunami. But the main causes of a tsunami is earthquakes. And usually it has to be an earthquake magnitude 7, 7.5 or greater to be able to be big enough to actually create a tsunami. So huge wall of water, huge wave that is displaced due to an earthquake, and usually it's going to be a convergent boundary. So you got two plates colliding, one goes underneath of the other one, and then when the earthquake moves, that tectonic plate gets pushed up and creates a tsunami wave. So here's your visual. We have two plates colliding. earthquake happens, and one side kind of rebounds and pushes the ocean water up in a vertical direction. Then it creates the tsunami wave that travels towards the coastline. So I'll just let this play through. So we didn't used to have a warning system for tsunami. In modern times, we have a warning system for tsunami. So if an earthquake that's large enough happens, there are all kinds of sirens and text messages that you would get and warnings for an impending tsunami. Where that came from is the fact that in 2004, we didn't have a global tsunami warning system yet. And there was an earthquake that happened the day after Christmas in 2004 in Indonesia. And that earthquake generated a tsunami, and that tsunami wave traveled to the coastline. And then it spread across the Indian Ocean, and it hit parts of Africa and India as well. And it killed over 250,000 people. So more than 250,000 people died because of this tsunami that occurred in 2004. What was unique about the tsunami is that sometimes the ocean will actually recede before the tsunami hits. What I mean by that is that if you normally have the crashing waves at the location that it's always at, what will happen is that the ocean will go back away from the coastline. And that's what this image is showing you over here. People didn't know that that was a warning sign for tsunamis during that earthquake or that tsunami in 2004. So they were like, oh, why is the beach retreating, or why is the beach getting farther away? And they walked out there, they followed it out to see what was going on. And then the tsunami wave came in and hit this island or this part of Indonesia. So we have the actual moment here. Here's the tsunami hitting in 2004. And then just to give you a sense of what it did, we have a before and we have an after of the same place. So basically there was nothing left after the tsunami. This is just an animation showing that tsunami as it traveled across the ocean. So it started here on the eastern side of the Indian Ocean, then it hit the area of Indonesia, and then the tsunami wave traveled, it hit India, traveled across the Indian Ocean, and then hit the eastern part of Africa. And again, as it did so, basically nobody knew it was coming, there was no warning. So even 8 hours later after that earthquake happened, that tsunami wave traveled all the way across the Indian Ocean and still killed people on the coastline in Africa because they had no idea that it was coming. All right, so just in case we're not familiar with a tsunami, let me see if I can speed this up. All right, hopefully this sound isn't affecting your ears in terms of the balance of the volume. All right, so what this showed us basically was that there's an earthquake that occurred. So let me just get back. Convergent boundary earthquake occurs, ocean floor gets pushed up, and then the tsunami wave travels to the coastline. So it can retreat. This is what retreat looks like. So the ocean will draw back away from the shoreline. It'd go out about a half mile or so. That's a key warning sign we now know of a tsunami about to hit. All right, and then as the ocean retreats and draws backwards, it basically gets a taller and higher wave that will come in as a wall of water. Okay, so if you're wondering about areas that are at risk for tsunami, it's anything that's in red on this map. So red has the greatest hazard. So in terms of the US, it's basically Alaska, Hawaii, and the Pacific Northwest. So the states of Washington and Oregon have the highest hazard for tsunami. But anything that's in red on this map, so all around Asia or the Pacific Ocean, in these areas, that's going to be high risk for tsunami. You got all of South America, the western coast of South America is at a risk for tsunami as well. So green here on the East Coast, we're good to go, unless there was some kind of asteroid or meteor impact. That would be the main cause for us to have a tsunami. All right, as I mentioned, basically there was no warning system after that 2004 tsunami that killed 250,000 people. Governments came together, put money together, a pool of money, and they established a tsunami warning system in the Pacific Ocean. So if there is a large enough earthquake that happens in the Pacific Ocean, there will immediately be notifications. There will immediately be warnings that are sent out to people. It'll go to your phone and it'll tell you exactly what to do if you're in an area that's at risk for being hit by that tsunami. So basically, each color dot here is a different type of instrument that's used to predict if a tsunami is traveling through the ocean, and then that's used to send out text messages to send a warning. Okay, so that's it for earthquakes. So we talked about a bunch of stuff related to earthquakes. We started with faults. We talked about magnitude, intensity, the types of waves, primary, secondary, love, and Rayleigh waves, and then we just finished up with talking about the earthquake effects. All right, so you should be able to finish your quiz that was associated with this lecture at this point, and then you also have a lab to complete for this week as well.